Hi guys. So in the last video, we described Newton's law of universal gravitation, and we also described how you could understand where the gravitational constant 9.81 comes from. And the form of Newton's law of universal gravitation is given by G, a constant, times the m1, m2, over the distance between the centers of the two objects. And this force applies to all things in the universe. G is a constant, Newton's constant of universal gravitation, and that's 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. In this video, I want to apply this to three situations. I want you to imagine you're sitting 6 feet away from someone, and we're going to evaluate the force, and it'll be a tiny number. That's why we don't perceive it in everyday situations. Similarly, I want to use properties of planetary motion and the fact that to good approximation, you can say that the planets travel around roughly circular orbits. They're really not circles, they're elliptical orbits. But for most planets, or many planets, the eccentricity is tiny. So we can use that to determine astronomical properties. So the one the two that I was thinking we could do is be to use the orbit of the Earth to determine the mass of the sun, and then we could try to use the orbit of the moon to try to estimate the mass of the Earth. The first one, the mass of the sun that we get, will be very accurate. The mass of the Earth that we get won't be quite as accurate. I assume it's just because our approximation of a circular orbit won't be as good. So let's get started. I want you to imagine that you were sitting next to a person. Let's just say it's equal to 2 meters. And just for convenience, let's go ahead and say that each person weighs 80 kilograms. Newton's law of universal gravitation would say that there is a very small gravitational force between you two, drawing you together. So let's estimate what the number would be in this case. You would say the force of gravity is G times m1, m2 over the distance between you squared. And if you plug in numbers, that would be 6.67 times 10 to the negative 11 times 80 times 80. So that's going to be 6,400 divided by the distance between you squared. 2 meters squared. And I'm just going to use the calculator here rather than do it in my head. So that's going to give me, type it all in, 6.67 times 10. Close it off, times, I can just do 80 squared divided by 4. And this whopping force is, dun, 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 I get 1.1 times 10 to the negative 7 newtons. Yeah, not that exciting. That's why we're safe. It just turns out because the gravitational constant is so small in everyday situations, we just don't even see this. And in fact, I'm pretending that the only thing around you, literally, the only thing around you is another person. In reality, you have air and you have furniture and all sorts of stuff around you, pulling you in all different ways. And so in reality, the real gravitational force you feel from everything except the Earth is much smaller than this because presumably it all kind of averages out to really small. So this is really just insignificant in everyday situations unless you have a mass comparable to planets and moons and things like that. Very good. To go over was to apply these same ideas to describe orbits of planets around the sun or moon around the Earth. And to do that, we're going to make an assumption. We're going to make a simplification rather than studying elliptical orbits, and that's a topic that you will learn how to handle. It should be in Calc 3, where you really go into how do you parameterize an ellipse, and there are all different ways to do it. And it's not hard per se, it's kind of just lots of little details to think about. So we're going to focus on circular orbits because it's simple. And it gets at the heart of the issue. So in this case, what we're going to imagine is, in particular, we're going to imagine we have a large mass object orbited by a small mass object. So capital M, not only is it capital and larger, it represents a larger mass. And what we're going to imagine is that the large mass is so much bigger it doesn't move enough to matter. So you can imagine that as the small mass goes around, the large mass is pulled with it a little bit, but it just kind of wobbles a little bit. It doesn't actually migrate very far. So in that case, we're going to assume that the large mass is at the center of the circle. We're going to assume that the small mass travels along the circle. And we're going to write down, well, we're going to draw a free body diagram. We're going to set equal to mass times acceleration. We're going to use circular motion and centripetal acceleration to come up with formulas, and we'll see where we end up. Okay, so the free body diagram for free body diagram for the little mass equals the following. Well, it's pretty easy. There's only one force. The only force acting on the small mass is the force of gravity. And that's it, because presumably this planet's out in space. So I just have to say that G, big M, little m, over the distance between their centers. So let's assume that the distances between their centers, I'll just call it R. And that has to equal the mass times the acceleration. Well, because it's a circular motion, we know the acceleration is v squared divided by r. For some problems, that's exactly the form you want, but I actually want to rewrite this not in terms of velocity. I would prefer planetary orbit. So I'm going to make another assumption, which turns out to be true, is that the speed remains constant as it goes around this orbit, which would be true for circular motion. So I'm going to assume that the speed equals 2 pi r divided by the period of the motion. So if I do that and plug into here, I get the following equation. I get G, big M, the little m's will cancel, so I won't even bother to write those, divided by the radius squared equals 4 pi squared r squared squared. Remember, if you have velocity squared, you have to square 2 and pi and r and t. So to square, that's why I get 4 pi squared. I'm going to go ahead and clean this up a bit, cancel some stuff out, and I'm going to just arrange this. I'm going to solve for the mass so we can deduce planetary and solar masses. So I'm going to rearrange this to say our main equation is that the mass of the large object, equals 4 pi squared r cubed divided by g times the period squared. So you remember in the last video, I described how Kepler's laws related the period squared to the semi-major axis cubed. Well, this is that same relationship rewritten just slightly. Because for a circular orbit, the semi-major axis is in fact the radius. So this is how, at least for circular orbits, you can confirm that Newton's law of universal gravitation it's just the arithmetic is more complicated. Okay, this is our main equation. I want to use this equation to calculate the mass of the sun. Okay, so our main equation is the mass of the central object, in this case the sun, is 4 pi r cubed over g times the period squared. So we need to evaluate these numbers for the period of the Earth's orbit in seconds. So how do we do that? Well, you could go through the process, 365 days, 24 hours a day, 3,600 seconds per hour, or you can remember Rent, the song, 525,600 minutes times 60 to get to seconds, or you can use Google or whatever. Okay, so we know these numbers. I went ahead and cheated a little bit and know that the period of the Earth's orbit is approximately 3.1 times 10 to the 7 seconds. The radius of the Earth's orbit around the sun. How could you figure that out? We've done this before when we were talking about the speed of the Earth way back, a month ago. What you could do is bounce light off the sun and count how long it takes for the light to bounce back to you. And you could cut that, since we know the speed of light, you could deduce the distances. So what we learned is that the radius of the Earth's orbit around the sun, again, cheating, is 1.5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 meters. Okay, and that just comes from timing and speed of light and stuff like that. And we know G is 6.67, as always. G 6.67 times 10 to the negative 11 Newton meter. It's just a straight plug and chug. What you calculate is 2.0 here. I cheated too, multiple ways, I suppose, today. Via Mathematica, I get 2.0086 times 10 to the 30 kilograms, which is, to be honest, I only type things into let's see, 3 sig figs. So really, all I can say is 2.1. The actual number, I believe, is 1.998 times 10 to the 30. This is our estimate. This is the experimental value. So not bad. Right? We're good to, just a whatever percent or so. a little bit less. So it is. So that's how you can stand in your, at your kitchen table and weigh the sun, is using Kepler's laws. And this is in fact how we measure all masses of celestial objects. We look at their orbital behaviors, and because we know Kepler's laws, and if you can time it somehow to get you reverse engineer or work backwards and get the mass of the planet. It works the same. So I really want to do the same exact thing now for the Earth, to find the mass of the Earth. The actual number is 5.97. We're going to use the orbit of this moon around the Earth to estimate what number we should get. So apply to the moon Earth system. So in that case, we have the mass of the larger object is the Earth. The mass of the Earth equals 4 pi. The radius you should use would be the radius of the moon's orbit, and that number turns out to be 363 times 10 to the 6th meters. Won't worry about units here. And so that's the moon's radius. E 6.67 times 10 negative. And the period. Well, what's the period of the moon's orbit around the sun or around the Earth? We know that there are approximately 13 lunar cycles in a year. So that tells you you're looking at something like 30 days. The actual number is 27 days. So you want to convert that to seconds. So you would have the period of the moon's orbit would be 27.3 days in particular, times 24 hours in a day, times 3,600 seconds in an hour, and you should square that quantity. So I did all that, typing it in Mathematica over here, just out of range of the camera. And the number it gave me was 5.09 times 10 to the 24. The actual number you might remember from the last video. So this is our calculated value. The actual number is like 5.9 something 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 times 10. So this is the experimental value. So the calculated value differs from the experimental value. I didn't do my homework. I presume it's just because the orbit is more eccentric. Can't speak today. It's more elliptical, right? The eccentricity is larger, and so our formulas then would be wrong. You really should go back probably and account for the elliptical character, which is going to change the details a bit. The other thing is, I assume the Earth is not nearly as massive as the sun. Probably our assumption that the Earth doesn't migrate isn't as good either. So you'd have to account for that as well. All right. Well, so if you follow that, you now know how to determine the mass of the sun, the mass of the Earth. You could do the exact same thing and look at the period of the motions of, say, the moons of Jupiter to estimate the mass of Jupiter. Really, the masses of all objects in space are inferred, they're all inferred using this idea. So, all right, I'll talk to you guys later.